First, a little remark. There's apparently something wrong in the schedule. It's promised the talk will be in Dutch, but unfortunately it will be in English. So I hope that's fine for everyone. Okay, good. So we're going to talk about writing high-performance code in .NET. This is my fourth talk today, or like this week. The goal of this talk is quite different from the other ones. All the other ones are very hands-on. We're going to take a look at code. This is actually my only talk with PowerPoint slides, because what I want to do is actually talk about some stories, war stories, of building a high scalable service in Bing, completely built on top of .NET and .NET Core, and we'll actually discuss the different pitfalls we ran into and how we actually solved those. So it's kind of like the case of the unexplained, by Microsinovich for Windows troubleshooting. This is for performance troubleshooting in the context of .NET. So I work on a service called Reactor. What it does is not that important. It's a huge scale service on thousands of machines, evaluating thousands of events per second across millions or billions actually of queries nowadays. So quite a big scale, all running on .NET on top of Service Fabric. And so what I'm going to talk about is like all the war stories that we ran into the last couple of years. Now, before I go there, I just briefly wanted to point out that when you have to build something that's high performance, that performance has to be ingrained into everyone inside your organization to actually value building a performance system that can reduce costs. When you have a cloud service, of course, can also improve, the perception that your customers have, all things. So the way to get there is to make sure that you measure early and measure often. It's not a good thing to actually start worrying about performance a number of years into your project and then say, oh, the whole thing doesn't scale, and then you have to change the whole design. You want to have a lot of instrumentation, so you know where the hotspots are in your code. Depends on what kind of application or service you build. If you build a service, you can use things like App Insights in Azure. There's a lot of different options to do that kind of stuff. And you also want to have, if you have very critical components inside your services or inside your applications, you may want to also benchmark those individual components if you really can prove that those are high volume and really impact the end-to-end performance. And then secondly, also establish a performance culture. That means that you will actually think about performance and reviewing all the designs, all the code, all the things you do. A good example of that is when you build a microservices implementation, that you want to make sure that the system behavior doesn't get negatively impacted when one of those microservices is down or gets upgraded. So you want to do things like fault injection, chaos generation, for example, to make sure that you actually figure out how the system behaves in the absence of certain other components behaving in a healthy manner. Okay, so that's just some stock advice. The slides will actually be shared. There's a lot of speaker notes at the bottom. Those are not speaker notes for me. They're just storytelling on like the deeper point I'm trying to make on those different slides. So you can actually also review those offline. Okay, first of all, know your tools. We have a lot of tools available that can help with performance, and I'm just going to go through them really quickly, and then we're going to get to the core of the talk. First of all, we have a lot of tools in Visual Studio, like memory diagnostics. Get familiar with these things, try to see what they can give you. We have a lot of other tools, like WinDbg for native debugging. Can be very useful if you have a service in crisis, you want to take a dump of a process, you want to see what's going on. You may want to get some familiarity with those tools and the commands, maybe to see what were the threads doing at the point the system was misbehaving. What are the CLR data structures looking like, for example, for thread pools, those kind of things. PerfView, who has used PerfView? Yep, PerfView is a tool built by the CLR team that can be used to analyze stack traces. Where's my CPU spending its time? What's the source of all those allocations happening here? Very powerful tool, very ancient UI. If something has an ancient UI, it's powerful, okay? Good. And then CLRMD, I'll talk about that one briefly as well in just a moment. But so first of all, the basics of WinDbg and SOS. I'm not going to go into too much detail. You download it, you install it, you attach to a process, or you open a dump, you run a couple of commands. This is the main command if you want to inspect .NET data structures. That's loading the Son of Strike debugger extension. and then you can run a bunch of commands, including bang help, to actually see what can I do here. So that's a native debugging story. Second, PerfView, download it, install it. It's X-copyable. It doesn't come with an MSI. It's just a zip file. You can drop it onto production machines to quickly check something if you need to. And you know, when you take a trace from a process, you will get CPU stacks. You can get things like heap allocations, and you will actually see we're allocating a bunch of strings on those code paths, and so you can actually see, you know, where the allocations are coming from, and try to mitigate issues that you see there. Okay. CLRMD. Who has seen CLRMD? No? Okay, that's a pretty new tool, and it's an important one to take a look at. Can also help in relation to .NET Core internals that I talked about. CLRMD is effectively the object model that's also used by the WinDbg extension for .NET, the Son of Strike debugger extension. So CLRMD gives you a complete .NET API which you can use to inspect all the CLR data structures. So you can actually build an entire debugger using this if you want. Now, that's not what you're going to do, but you can actually write code that allows you to, for example, traverse the heap and say, I would like to see all the customer objects on the heap and why those customer objects are referring to those things, for example. You can build domain-specific tools to actually go over the dumps of your process, which is very hard to automate in WinDbg because that's a textual interaction. You get text out of a command and then you have to do a new command. So you have to do text parsing and that kind of stuff. This will expose, for example, the heap as an IEnumerable of CLR object. If you want to go over the heap, do that. And then you can look at every object and you can walk the heap. You can sort of play garbage collector by tracing pointers, all sorts of beautiful stuff. So you can build little tools, and I will show you one of these later that we built to analyze the sockets opened by a process by looking at all the socket instances and printing the IP address fields, for example. Okay. Now let's actually now talk about a couple of war stories. The first case I want to talk about briefly is the case of the trace. I actually said, you know, we should do a lot of logging and instrumentation to know what our code is doing. We actually were using trace source at some point. I guess a lot of you have used trace source before. Yeah? No? Some? Yeah, System Diagnostics trace source was kind of the way of doing tracing. You can register trace listeners. And at some point we actually ended up seeing a lot of CPU being spent and a lot of log contention also taking place on many threads. And we actually looked like what was going on there. And so if you have non-thread safe listeners registered with the trace source, we actually have some global section in there, a global lock, that actually will cause all of those loggings to actually bounce on that same lock. And now the second thing that actually happens here is that we pass down the string format, and the arguments for the event that you're trying to trace is getting passed down to the listener. So what's also happening is that under this lock, some things may actually take the format string and actually do the formatting, which causes string allocations. So this lock can be long-lived. And that only happens if you have listeners that are not thread safe. And so what happened is somebody made a config update, registered a new listener to that, which said this thing is not thread safe anymore, like was a listener that couldn't be talked to concurrently. So the trace source infrastructure introduced a global lock. This if use global lock is basically a Boolean predicate that's evaluated by looking at all the listeners. And so at that point, performance just went completely down the drain just because of a small config update. So be aware of tracing and check whether you actually have listeners if you use trace source that are thread safe. Okay. Now, second thing here is the meta point is always be aware if you do logging with strings and params arrays. It's a source of allocation. At some point, that format string has to be expanded into a message, and the question is like, where will those allocations happen? Will there be too many of that? Will you cause a lot of background radiation in your service because of string allocations? And especially if those happen under locks, then you're off to the races for sure. So short term, what we did was actually tweaking the listeners and also thinking a little bit more about the verbosity levels, because we had a lot of things being logged that didn't have to be logged all the time. So we worked with the verbosity levels of warning, information, error. And long term, we actually moved to event source, which I'll talk about in just a moment. And that moment will be in after this section. So the second thing that we actually ran into at some point was huge exceptions. Exceptions are pretty interesting because they indicate something's wrong in your system, so you may actually want to log them, but you have to be a little bit careful because toString is a virtual method. So when you call toString, God knows what's happening. And in particular, when you do toString on an aggregate exception, a lot of stuff can happen. So what we had was one of those microservices hosting about 1 million computations, and we were restoring those computations in memory after failover of a machine. So we are loading those things, and all 1 million are sort of being instantiated by separate tasks. It's not really as fine-grained as that, but you know, lots of tasks being created, and we sort of concurrently wait for all of those things to be done. But at some point we sent an interrupt signal to that thing saying stop doing that, because Service Fabric decided, oh, we were promoting you to primary, but we have a primary elsewhere. Please cancel promoting yourself to primary. So that whole thing got cancelled. Result being an aggregate exception with 1 million inner exceptions, each saying, I've stopped doing my work here. And then what we do was doing a string.format on top of that and a toString, result being a single log file of 100 MB with, you know, a single toString output, you know, 100 MB of stuff just for that single condition. Now, of course, this was also coming together with the case of the trace. That was the thing happening under that critical section. So all the other threads in the process were just waiting to log their stuff because we were doing this massive thing with a lot of string formats, lots of allocations, lots of garbage collections, holding up the whole world effectively. So beware of, like, you know, what you trace. If you trace things like, for example, exceptions, know the domain of the exceptions. Can you expect those monstrosities? And in general, it's actually good to know the kind of exceptions you're tracing, because in some cases you may be, for example, writing a target invocation exception, which is useless unless you also, you know, print the inner exception of the target invocation exception, which contains the real problem. So, you know, think a little bit about, like, blindly writing every single exception.toString into log files. You may actually end up in pretty bad situations. Okay, so that's what we did. We actually special cased a bunch of exceptions and actually dealt with it, knowing what could happen in certain places of the code. Now, another thing we did is actually move to event source. If you haven't looked at event source, you definitely should. Event source makes the use of event tracing for Windows relatively easy. ETW is a very high performance tracing infrastructure built into Windows NT. It's actually using a circular buffer in kernel mode, and so there's a lot of stuff happening under the hood to make those things really fast. And so you actually again have a producer-consumer model. You can write to that, and then you can have listeners which can be out of process listening to these things. And so something we do quite often is making sure that we just write to ETW and then have a background process, typically deployed as a Service Fabric service, that listens to those events coming out. The result being is that all the voodoo happening for tracing is not happening in the working set of the service itself. It's happening in a separate process. And so now if that process somehow, you know, inflates the thread pool or blows up everything, like, no harm done to the service. You know, we sort of have that thing being isolated through just a very small message passing system, which is ETW. Okay, so the basics of event source is very easy. You derive from an event source like this, and then you write a bunch of methods, and you can call base class methods called write event. And especially if you use, you can also put a bunch of custom attributes to add keywords and tasks and opcodes and all sorts of things, but this is the simplest thing you can do. And so here I have request start and request stop. If you suffix things with start and stop, you get a beautiful way to get insight into that component. Why is that? Because start and stop gets correlated regardless of the threading. If you have async APIs and all that kind of stuff, it doesn't matter. We will do all the correlation for you. And so if you actually end up looking at something like PerfView to a process that uses start and stops, what you see over here is that those starts and stops actually are correlated. You see an activity ID on the right hand side, which will be prefix based, and so a start at the beginning of some piece of code followed by a stop at the end of a piece of code, no matter how many asyncs and awaits and stuff you have in between, will be related to each other. So out of the box you get something that measures the latency between the start and the stop for every invocation. On top of that, if you actually have nesting, so for example to serve a request you want to do some authorization, authentication, you want to go to another service, you want to go to a database, you will get a tree of things here. So you just sprinkle in starts and stops, and you can follow every request, seeing, you know, what time was spent between start and stop in the database, what time was spent between start and stop one level out. We do all of that relationship tracking for you by introducing those activity IDs. And so a very powerful mechanism that also gets rid of a lot of stopwatches in your code. Like otherwise you have stopwatch start, stopwatch stop, blah blah blah, causes heap allocations, a lot of voodoo that you have to deal with. So if you haven't looked at event source yet, take a look at it. You know, there's a lot of blog posts on the .NET blog that explain how to use this. It's a very powerful tool. In fact, the default tracing in Service Fabric uses event source as well. On top of that, the data is actually very structured. It's not just strings. If you build good tools on top of that, and we have a bunch of tools, you don't have to do string parsing in your logs anymore, because you're saying something like user ID 15 arrived at that datetime, and spent that much time in the system. It's not going to sit in a string. You can also print it as a string, but you will have those fields statically typed, so you can write things like link queries over those events as well, using tools like link to traces, which is based on reactive extensions. So very statically typed, high performance mechanism to do this kind of stuff. Okay, another case. The case of the stuck finalizer queue. This happened, you know, one day, a total inconvenient time of the night, of course, where, you know, the service was becoming very sluggish. So we had to take a look what was going on. And so one of the first things you want to do, often when you're diagnosing a system that's very sluggish and it's using .NET, I typically issue like 4 or 5 commands in WinDbg to sort of see like what's going on. And one of the ones that I always use is finalize queue, to see like what objects are on the finalizer queue. And the finalizer queue is the thing that deals with, for example, clearing native resources because you have lost reference to an object. The object is garbage collected and it holds on to, say, a file system handle. And so what we saw is that we had 82,000 objects ready for finalization. And if I check this thing again, 10 seconds later, there were like 90,000 or something, and, you know, nothing was making progress. So there can be a couple of things here. Either something that needs to be finalized takes a long time, or the finalizer queue is completely stuck because the thread doing finalization is not getting any time to execute, or it's deadlocked. And so we looked at the finalizer thread. Well, I did that one step after this, but I also looked at the finalizable objects, and what we saw over here is things like 4,300 thread instances are kept alive. Yeah, well, those things are also finalizable resources. If the finalizer doesn't run, we don't get rid of the native resources. There's this thing called conditional weak table, which has weak references to entries in a table that caused a massive memory leak because the finalizer was not running, so those weak references were not being cleared either. We were holding open 627 sockets that didn't get time to talk to the WinSock API saying close the socket and forget about it in the Windows operating system. So we ended up with a whole bunch of resources sticking around because the finalizer was not running. So then looking at the finalizer, we actually saw that there was in fact a blocking wait on something happening in a library called 0MQ. We could even blame the user because 0MQ was built by a guy called Johnny in the open source community. We were not able to find Johnny, unfortunately. So we had to do something, look at the code, you know, issue a report and those kind of things and fix this. But so that's a very important thing to realize. If you have a high performance system, you know, and you have a lot of, you know, external libraries you're using, it suffices for one of those libraries to be misbehaved, causing massive issues. And so that's what we saw in this particular case. Okay. So the finalizer, very precious resource to take a look at. Now, don't forget, once you solve it, that it can't happen again. The worst thing to do is like the next time, this was so unlikely, you were so lucky to find this thing. Next time something goes wrong, you know, believe me, like, you know, do the same things you did last time. There's a high chance that you see something similar. And in fact, that happened indeed. This is another case, you know, where exactly the same thing happened. What happened was that we added some instrumentation to say, like, whenever there's an unobserved task exception on the task scheduler using a global event handler on task scheduler dot whatever, we registered an event handler, and when one of those unobserved task exceptions comes, we're actually going to write to some internal system called DM, which is a monitoring system, And it turns out that thing is implemented using synchronous I/O. This was not deadlocked or anything like that. It was just making the whole finalization process super sluggish because we were doing synchronous I/O on the finalizer. The reason this thing runs on the finalizer thread is because this actually uses a finalizer in task of T that says if nobody has seen the exception on the task and I'm being finalized, I'm gonna raise that event so that somebody has a last chance to look at it. And we can either crash the whole process in case you're not happy about that, or we can actually run some custom code for you to log things. So that's what we did, and that runs on the finalizer. So in this case, you know, everything became very sluggish, and you can already guess what's happening in that case. Things were getting sluggish. The result of that being that things were timing out, causing other exceptions to be unobserved, causing even more sluggishness because we end up in the same code path. So this was just spiraling out of control, you know, second after second, so we had to do something about it as well. The answer in this case is, well, beware of what you do in things like unobserved task exception handlers and those kind of things, because if you have something blocking in there, you know, it may be happening in an inconvenient spot, and unfortunately, you'll only see that when you hit it, of course. Okay, so unobserved task exceptions, they don't crash the process anymore, even after we introduced async and await, because, you know, there's a lot of cases where people, you know, just don't observe exceptions, especially if you do async void methods for event handlers. You know, you don't have a good way of observing task exceptions. So we changed the default on task exceptions, not taking down the process anymore if you don't observe them. And so they can be a hidden source of performance issues, as everything exception related can be. So what we now do is in debug builds, because we don't use async void everywhere, anywhere, it's plain dangerous to use that, and if you don't have a UI framework that forces you to have async event handlers, you don't have any excuse, you know, to have async voids in your code. So in debug builds, because obviously we don't want to take down the service in case something is wrong, but in debug builds, which we run in pre-production environments, we actually turn on this flag to revert to the old behavior and actually fail fast in the process in case we have one of those places where we have unobserved exceptions. We want to have control over all of them and observe them. Now, what often happens is that people write something like this. Await task.whenAny between a delay and some operation. In case the delay happens first, often you don't do anything to see whether an exception would eventually have happened on the foo async. Maybe you try to cancel that by passing in some cancellation token as well. So you can consider doing a little bit more work, because you may still be interested in the fact that that thing completes at a certain time. It's not because you time it out that it's not running anymore. You may want to see what the latency characteristic is of that thing that eventually will stop running. So you may want to attach a continuation anyway, and also see what the outcome was of that operation. Like, why did it take that long? We had to time it out, it took 30 seconds. Maybe after that it just reports an exception saying the target service I'm talking to was not available. So you want to do some logging anyway in there. So, you know, if you do this idiomatic pattern of timing out some asynchronous operation, you may want to sort of construct it a little bit like this, where you allow that operation to be cancelled, and in case you hit you know, completion of the delay prior to the operation, you try to cancel that guy, but you also don't just fire and forget about all of that stuff. You actually attach a continuation to foo to see the eventual outcome that will happen asynchronously whenever that happens. Okay, so that's something we did religiously in all places in the code to make sure that we don't let those things fall through the cracks. Next case, costly timers. What we had at some point was a huge contention on timer queues. That manifested itself in the inability of like having timers being fired at the right time. All sorts of things that had to do with system threading timer were suffering some issues. And so what's really happening inside the timer code in the BCL is that timers have some locking on the app domain in order to sort of maintain the timer queue in 3 cases. And we need to do something with locks in case we have to fire a timer, also when we change a timer and when we close a timer. Okay, so those are the 3 places where we intersect with some lock, this global lock called the timer queue.instance. And there's a bunch of optimization around it to make sure that we don't spend too much time under that lock, of course. But so there are some assumptions, and now that the whole framework is open source, you can actually see what the assumptions are of those things. So in this case, the assumption is that timers are created and destroyed frequently, but rarely actually fire. Okay, people create a lot of timers, but they may cancel them before anything has to happen with them. And so we had another case where we actually ended up creating and deleting a lot of timers, but we weren't deleting timers we didn't care about anymore. They were just sitting there. So we ended up in this situation where rarely actually fires was no longer true. And so like we have a lot of cost under the lock for firing timers here. And things have been improved quite a bit over there. Now it's important to realize that things like task.delay actually use this thing. And what people often do is they use a task.delay to time out an operation, like I showed just a moment ago. But a task.delay can also be cancelled, which means if the delay is no longer needed, you can cancel the underlying timer. But we weren't doing that. So for every single operation, we were actually saying, I want a timeout of, in certain cases, 200 milliseconds, 500 milliseconds, like for very high frequency events. And all those timers would eventually fire just to wake up a task saying, I don't need the result anymore because the operation already completed. So the better way to do this task.whenAny with delaying a certain operation is also to have a cancellation token to the delay operation. So when the operation that you're timing out completes first, you can cancel the delay, which will actually do a dispose of the underlying timer and not let that timer eventually fire. Because what's happening here, if you have long delays like 60 seconds, you will see the performance issue 60 seconds after success. So if you have a request burst, oh, all those requests went really fast. Why was the system so sluggish 60 seconds after serving 1,000 requests? Because those 1,000 timers were firing and actually blocking the ability to create new timers or dispose existing timers because they all use the same lock. And so that's one thing you can do. In other cases, if you have fuzzy timing requirements like 30 seconds is okay, 28 is fine, 32 is fine, you can also do things like timer coalescing if you really have a lot of these things. But so that was like a very simple fix for that type of issue. Another case, acquiring all the locks. Saw that over and over again. It's not because you have something like a concurrent dictionary that we never have locking. Concurrent dictionary, concurrent queue, concurrent stack, all those data structures actually have fine-grained locking. We try to put locks on small buckets, but there are certain operations on those data structures that require to acquire all the locks at once in order to get a consistent snapshot of the world. And a good example of that is count. We had some little piece of code somewhere that was just checking, is the dictionary not empty? If the dictionary is not empty, we're not going to do anything. So it was just if dictionary.count is 0, return. Like that thing just undermines the whole concurrency aspect of the dictionary because that thing will acquire locks on all the buckets so that no bucket can change and we don't end up with overcounting or undercounting or anything like that because we snapshot one bucket having 5, another bucket having 4, and then the first bucket gets a couple of items added or deleted, and we would end up with a number that's not reflective of reality. And so we actually had this thing happening under some timer somewhere. Again, this thing was happening under a timer, under another lock, more lock contention happening. So beware of how certain things work. Things like count on a concurrent dictionary, if you just think about it. How is this thing going to get the count? Either they maintain the count for every operation, or that count is lazily evaluated. And in that case, well, if there's fine-grained locking and you need to do a count, how can you do that to get a consistent number? You need to lock everything. Documentation actually explains that as well, but in some cases people just put in .count somewhere. And this was actually a case where people changed the dictionary to a concurrent dictionary to solve some other issue, and the count check was still in there. Okay, that was also something pretty bad. Now this was a beautiful day. I remember that day very lively. I was DRI that day, and I got called by Satya. It's an automated voice message, from our internal service saying like, we appreciate, you working hard for us even at 3 AM in the morning. Something's wrong, the customer is blocked or whatever, like very generic message. But so yeah, that wasn't, providing me with any comfort at all. So I had to log into the system, and I came to the conclusion, well, no I/O is happening. Like, everything is just not talking to each other. And so what the heck is going on here? If you see something like that, again, I did my ritual. Finalizer queue healthy, answer, yes, everything good there. Okay. At that point, I was getting worried because it was not a repetition of something I knew. I can fix this quickly. Thing, bang, thread pool. So I looked at the thread pool and I saw, the completion ports, which are used to serve the completion of asynchronous I/O, for example, we only have one free completion port thread, and we have 300 or 836 that are currently working. So the logical next thing that I did at that point was just take a look at what's going on those 836 threads, and you can already guess they're all sort of waiting for some resource. Like, a lot of these things have to do with locking. And so I was actually looking at that, and you see over here a very similar thing to the themes I was talking about a moment ago. I saw this kind of thing here, jet_util_monitor contention. It has the word contention in it, so likely it's a monitor, which is a lock being contended, so there's a lot of requests on that same lock. This was a case of, again, printing exceptions, very similar to something I talked about before, but there's one thing I wanted to point out here. Sometimes people come to me, or I explained this thing, and they said, well, I looked at the graphs in our monitoring environment, and you say there was thread contention and nothing was happening, but the CPU was still high. Why was the CPU high? Contention should mean that everyone's locked and there's only one thread that can do some execution. The answer to that question is that contention in the CLR is implemented in an optimistic manner. There's contention, let's hope that we don't have to park this particular thread, and let's spin a little bit to see whether that lock becomes available rather quickly. So we're actually going to do some spin weight in the aware lock contention code path over there. So like all those threads were still doing some CPU trying to get to that lock to eventually say, oh, I'm giving up on this, I'm going to park this thread. But in the meantime, another thread came, and like that thing would also try to enter that particular code path. So we actually ended up in this kind of situation. Now, question of course is like, why were we doing all of that logging? And that logging was not done by us. What was really happening, and this is actually the code that you can find in the core CLR with try spinning and yielding with some arbitrary number in there, which was at some point measured to be an optimal thing for certain workloads. So that's the spin lock. I actually forgot to put in some detail here, but what really happened was that some app.config file got updated to have some verbosity for tracing in WCF being set to maximum. So it was kind of running in debug mode, meaning that for every exception, we want to send the whole stack trace to the caller, so the caller can actually log what's going on in the service. So it was actually a config change that caused this. Just looking at the call stack, I actually was able to figure out that it came from system service model internals. I looked at that code, which you can find on source.net, saw that this thing is influenced by a certain flag in the config, did an update to the config, and the problem went away in a couple of minutes time actually. So it was a pretty quick find, but again, just looking at the stack trace, looking at the thread pool, figuring out what's going on, lock contention, who's causing it. If you have lock contention, don't just stare at it and say like, this code is bad, there shouldn't be that much locking. Think out of the box, like step up a little bit and see, like, why do we reach that code path? It's easy to zoom into that and start just complaining like an old guy sitting in a corner being grumpy. In my time we had fine-grained locks, like why did they do that over here? No. Zoom out and say like, wait a second, why is WCF for every single exception here going through that code path? Like maybe it's not the exception printing code to blame, because that has to create a lot of strings anyway. Like, can we not avoid that kind of stuff happening here? And the answer was just a Boolean config flag flip from true to false. So pretty embarrassing kind of situation that thing ended up in production. But you don't know until you see it, of course. Okay. Singletons. Very small one. The BCL has a lot of capabilities, or like places right now where we do optimization of memory. Good example is arrays that are empty, task.from result, for just a completed task. For all of these things now, we actually do have singleton instances available, which can actually reduce a lot of background radiation, as I call it. Like in the past, we had some code paths, and we're doing task.from result everywhere just to return a completed task out of some stub API. Like, as opposed to allocating new completed tasks everywhere, you can now use things like task.completed_task. If you need an empty array, you can use array.empty of t, and you get a singleton instance, no allocations needed. So you can actually reduce a lot of that like fine-grained allocations, which, you know, if you run into that for a high-density service, you know, it can be worth, you know, fixing. In fact, a lot of stuff in .NET Core, people have gone through all of the code over there to avoid, you know, places where we do new int square bracket 0. No, that's now array.empty of int, like, you know, so that we don't have to allocate empty arrays all over the place. In fact, the C# compiler nowadays, when you call a params method with no arguments, it will actually use array.empty over there, if that's available in the target framework that you're using, starting with 4.6 something. Okay. Another thing, that's a caveat that hopefully some of you are aware of, but if you have a static singleton, like say a static read-only field, or like in this case a read-only or get-only property, and you put that in a generic type, that for every instantiation of that generic type, you will actually have a unique instance of that singleton. So like, you know, if you have a foo of int, and or in this case a bar of int and a bar of string and a bar of double, you will have 3 foo instances which are claiming to be singletons. And so if you're going to close bar over a lot of types, especially dynamically at runtime using reflection, let's say let's create a new bar of t where the t is something I just learned about, in that case you may end up creating a lot of singletons and not really having singletons. So you may want to put that outside generic types if you really want to have one that's not dependent on t, but just, you know, one single shared singleton. Okay, boxing. Another case that we ran into, there's a very good reason that we say when you implement a struct, override equals and get hash code. Why? If you don't do that, we actually have to call those things as virtual methods on system.object, which requires us to do some boxing. We need to box that thing in order to go to the virtual dispatch table, all that kind of stuff, to end up in the implementation of system.object. And so override, you know, equals and get hash code, you will get a lot of benefit out of that if you implement structs, especially if you put that struct in, for example, the key of a dictionary, which constantly is asking for get hash codes and those kind of things. So override equals and get hash code on structs, and also be aware of things like, you know, passing those guys to things of type system.object in a params array, for example, causes boxing, which causes, you know, garbage collection, which may not be bad if you don't do it frequently, but if it's on a high frequency code path, you know, boxing can actually be quite expensive. This is the right way to implement, you know, the equals and get hash code using equality compare.default for all the fields you have to put get hash codes on, for example. In this case, this was a recursive situation where we were doing this.bar.getHashCode. So we're calling getHashCode as an instance method on bar, which is an enum, which doesn't have an overridden getHashCode. So actually doing an equality check or a hashcode calculation for foo was doing double boxing. We had boxing happening initially, you know, just on foo because we weren't overriding getHashCode here. Once we overrode that, we were still doing boxing on this.bar because it's an enum, and so the better way to do that is by using equality compare of bar enum.default and call .getHashCode on top of that one. So the best thing to do is actually always use equality compare of t.default to sort of, you know, recursively calculate hash codes and equality relationships of your fields in a struct, for example. Okay. I'll skip this one actually because I want to get to a couple more things. I'll get rid of the read-only thing. Not too important, the read-only thing. One thing that's, I think, very underestimated in its power are immutable data structures. In a lot of cases, people just add additional complexity by assuming that something will have to be concurrency safe and thread safe and support mutation, hence we need to do some locking. Maybe the solution is to use fine-grained locking, and they go down that entire path of saying, let's assume mutation has to happen. Now we have a lot of APIs nowadays that actually use immutable designs. If you look at Roslyn, for example, all the abstract syntax trees in Roslyn, whenever I'm typing code in Visual Studio, we're generating immutable syntax trees. We don't want concurrent edits to that. And the beauty of that is that you don't have to worry about synchronization. Those data structures can be handed out to any thread and they can all party on it to read it. If you want to do a mutation, you just create a new copy, which can lead to a lot of allocations, but in a lot of situations, you can reuse a lot of the data structure. For example, ASTs in Roslyn. If I just add something like another member to a class, I don't have to generate a new expression tree or abstract syntax tree for all the siblings to that method. I just have to create a new spine of the tree. I can create a new tree representing the new method. I can create a new tree representing the class in which that method sits, but all the child pointers can refer to existing trees for all the other methods I already had. So you also get, far less copying because you can actually reuse a lot of stuff. And so we have things like immutable collections, system.collections.immutable, which actually use that and can be super useful in certain cases. And so this is how it actually works. You have a builder. You go through the builder to actually create a list or an array in this case. So you create an array, and when you're done with it, you do toImmutable on that. And at that point, you can't change that array anymore. Which also means if you then go to the array and you say, I want to change something, you can actually reuse a lot of stuff. Say you change, the first element or something, we can actually reuse whole sections of the array, point to those sections, and sort of insert in a new data structure the mutation you made. And so that's completely concurrency safe. And it also allows you to do something like this. This is the last one I want to talk about here, a very concrete case we ran into at some point. Again, the situation of a configuration manager. We had something that centralized all the configuration manager in our service. So that's the place where we would go and look up settings. And of course what was happening is that some subcomponent for every request was going to the config manager to read some configuration. And we saw a lot of log contention over there. Now those settings were backed by data coming out of some configuration system that we wanted to abstract over. Maybe it's an app.config, maybe it's a service fabric configuration stored somewhere. Like, it doesn't matter where it came from. But so the settings get reloaded whenever something is changed. In that particular example of the day all the I/O stopped, that's the way I actually changed the config to say WCF logging enable true goes to false. It was just picked up by that configuration manager and was effective immediately without restarting the service. But so what was happening was that whenever we went to that, we saw some locking costs. And so we looked into it and we actually came to the conclusion, well, this seems to be written quite smart already. Like somebody had taken the time to say, we need locking around the dictionary. Maybe I could use a concurrent dictionary here. They did some testing with that. It didn't really help too much. So they landed on a reader-writer lock slim. And for all the reads, they would use a read lock. And for the refresh, they would use a write lock. And there was still a lot of overhead to this thing because there was such a high frequency of calling to that thing. There was just overhead that we wanted to try to avoid. And this was not causing any service outage. It was just causing performance degradation. So it wasn't the most high priority thing to look at. But at some point in PerfView, during a sunny day, we took a PerfView and the top thing was actually configuration manager. And then you start saying, well, I would rather see things there that deal with processing events, because that's what we do rather than reading config values. So we looked at this code, and in this case we just had to rethink it. We had to rethink our assumptions, which is a very important thing to do when you look at performance issues. What's the assumption here? Well, there will be frequent reads, that's good. There will be occasional writes. Question, how occasional? Once an hour? No. Once a day? Maybe. Once a crisis, every other day. Yeah, so it was more like in the order of magnitude of hours to days, rather than, a couple of reads and then some write, a couple of reads and then some write kind of thing. So what we landed on in this particular case was, we don't have to do any locking whatsoever. Let's just create a configuration manager that holds on to a dictionary containing the current state of affairs, do publication of that one, meaning we're not going to mutate it anymore, we're not going to do concurrent edits to it, all the reads go to that dictionary. And then when we have to refresh the config, we're just going to create a new dictionary and throw out the old one. Result, that thing never showed up anymore in any of the performance traces. It was such an easy thing, the code got much simpler, we got rid of the entire lock altogether, just because we stepped back for a moment and didn't sort of like go into that code and looked at it and say, oh, a reader-writer lock is not cheap enough yet, let's actually go to the CLR team, complain about that thing. Like, again, you know, step back one level and think about it. Like, okay, how frequent are the writes? Very infrequent, you know, like once a day or something. So we just did that, and you know, that thing never showed up anymore. Okay, so with that, that's actually, you know, the takeaway of that one. With that, I'm at the end of my talk. This is not the end of the deck, but I've given this talk at other places before, where I actually had the order slightly different, so you can actually find videos where I explain the other things as well. And secondly, there's a lot of documentation at the bottom of those slides, as you can see over here in the speaker notes, where I sort of talk through that issue. So I will actually make sure that those slides end up on the website, or whatever the way is that we share things over here. Feel free to take a look. Feel free to drop me an email as well at bartde@microsoft.com if you have any questions. I'll stick around, so if you want to come over to ask some questions, you're more welcome to do that. And I hope to see you later in my last talk about Roslyn, where we'll actually play with immutable abstract syntax trees all the time. Okay, thank you.